Hello everyone, welcome to the electromechanical devices course. Today's lecture we're going to continue the chapter 2 that we started before. We have discussed so far three steps or three methods of the resistive circuit analysis, which are the Kirchhoff voltage law, current law, and Ohm's law. The second method that we already covered, the series and parallel equivalence, and how we can make use of the equivalent resistance of set of resistances that already distributed within an electrical circuit to use this equivalent resistance to do some analysis for an electrical circuit. Then we discussed the node voltage analysis in the previous meeting. Today we're going to consider the mesh current analysis, and this is going to be the last method that we are going to consider through chapter 2 for the resistive circuit analysis. So the mesh current analysis method, it is very simple method actually. It is another general approach that can be used for electrical circuit analysis. As we mentioned before, that the Kirchhoff voltage law, Kirchhoff current law, these are, and Ohm's law, these are the main three laws that we have to use them to do analysis for an electrical circuit. If we're gonna talk about the other methods, like the other three methods, definitely they had been driven, these methods have been driven from based on the Kirchhoff current law and voltage law and Ohm's law, and this is what we discussed for all of these methods before. Like for example, the equivalent series, the equivalent resistance method, we drive this method itself or the procedure based on the Kirchhoff voltage law and current law. The same thing for the node voltage analysis. Here also I'm going to show you how it is related to this, the mesh current, how it is related to the Kirchhoff voltage law and current law. Everything is related to these laws because these are the fundamental laws of the electrical engineering in general. So, and as we mentioned, to do an electrical circuit analysis in this course, analysis, it means that is to find the unknown or find the sum of the requirement, that we are interested in one or two or three parameters of the system. So to come up with these parameters or find this parameter, this is the meaning of the electrical circuit analysis. And we said that these unknowns or this parameter would be in the form of a voltage or a current in many cases. But if the unknown is a resistance, we said that this likely to be like you already doing design of the electrical circuit more than being to do analysis of the electrical circuit. Anyway, for the mesh current analysis method, again, it is another general approach of electrical circuit analysis. And this approach and the first two methods, for example, the first step, if you remember that the first step was to distribute the current over the electrical circuit. In the first method, Kirchhoff voltage law, and the same thing for the equivalent resistance. What was the first step? The first step is just to distribute the current through the electrical circuit. When we distribute the current, we already identifying the current over the different branches. Or over the different element, because any element within an electrical circuit, it should be located over a branch. So what we were doing is just to distribute the current starting from the source, which would be like a current source or a voltage source, and just follow the structure or the arrangement of the different element and just distribute the current through the electrical circuit. This distribution of the current gives us the current over all the branches within the electrical circuit. But the mesh current method, it is a little bit different, that we're gonna skip this method, that we will not distribute the current through the electrical circuit. Also in the node voltage analysis method, we didn't distribute the current over the electrical circuit. So, and instead of distributing the current over the electrical circuit or over the branches, we're gonna identify mesh current, and that's why we do have the name. So what is the difference between the mesh current or the current over a branch? This is the difference between or the mesh current analysis method or the previous two methods, the first two methods that we explained before. So here we will not gonna distribute the current over the electrical circuit. Instead, we're just gonna define some mesh current. So what is the difference between circuits with branch currents and circuits with mesh currents? This is a circuit with a mesh current, but this one is with branch current. So for example, if I give you this problem, this electrical circuit, and I ask you to use the Kirchhoff voltage law, for example, the first method to do analysis for this electrical circuit. The first step was just to distribute the current through the electrical circuit. So we used to start from the source, which let us assume that the current over this source was generated by this voltage source is just I1. Then this I1 will go through the first resistance. Then at this node, we're going to have here a node, right? At this node, the current will be split into two parts, into I1 and I3. And according to the Kirchhoff current law, that the sum of I1 and I3 should give us the total current, which is I1. So here we are doing distribution of the current. We are distributing the current through the electrical circuit as given here. And you should understand that the current over this branch or this resistance is already located over a branch. So we're going to say that the current over this electrical branch here is I1, the current over this electrical branch here is I3, the current over this electrical branch here is I2. Make sense? So it means that this is what we used to do, especially for the first two methods. But how about the mesh current? The mesh current is a different approach. Like we identify a loop, like the same way that we define the loop using the Kirchhoff voltage law, right? But here, we're gonna give it a name like a mesh more than loop. Why? Because it is related to the current, not related to the voltage, as we did in the Kirchhoff voltage law. In addition, the loop in the Kirchhoff voltage law, it is a different concept than the mesh current method or the mesh that we're already identifying for the different currents here. So the mesh current method, it depends on identifying mesh currents. So this current I1, for example, if I ask you, initially you're just going to consider like would you have one loop and another loop, like one loop and another loop. But this one, to be accurate, this should be mesh 1 and mesh 2. So this is mesh 1 and we do have mesh 2. So for example, in the loop, we used to have, for instance, for the loop, we may have like loop 1, loop 2, and there should be like loop 3 that go all over this, all the circuit, and we're gonna skip this branch, right, for the electrical circuit. But here, we cannot do this thing. Basically, we should identify I1 and I2. This is like one loop and another loop, one mesh and another mesh, but there is no mesh in this way. So that's why we do have different names here. We are using different names because we cannot define a mesh over the circuit and we skip this branch as we used to do for the loop, for the Kirchhoff current law, voltage law. So that's why we are going to define I1, mesh 1, and we do have for this case just only two meshes, mesh 1 and mesh 2. And your objective is just to define a current that already roaming within this loop, within this mesh. And there is another current which is I2 that already roaming or rotating or moving within this mesh. If you remember in the beginning of this class, the current, it is the speed of the flow, related to the speed of the flow of the electron, how fast these electrons are moving through these electrical conductors, right? These electrical elements or over these branches. But here we are identifying the current, which are the speed, which define the speed, how fast the electrons should be moving within this mesh, how fast the electron should be moving within this second mesh, right? But for example, if I ask you how much is the current over this branch, this current I1, I2, it is not a branch current. So for example, if I ask you how much is the current over this vertical branch, over this electrical element, it isn't I1, it isn't I2. It will be the difference or it would be the sum. It depends on some aspect that we're going to consider right now. So anyway, it means that this I1, it is not necessary to be the current over any one of the branches within this mesh. The same thing I2, it is not necessary to be the current over any branch within this mesh. So these are the currents through the mesh. These are the currents through the mesh. You can assume that these currents, I1 and I2, like set of electrons, group of electrons, already roaming in this area. There is another group of electrons that roaming with a different speed within this area, within this branch. Make sense? So you're gonna find that there are some electrons going in one direction. There are some electrons that it is looks like this way, that there are some electron going in one direction and there are some other electron that should go in the opposite direction over a certain branch. So it is like you do have a group, like we already grouping the electrons. It is not physically possible that you do have electrons going in two opposite direction, but anyway, it is looks like this way. You can consider it in this concept, like we do have a group of electrons roaming in one direction or roaming with a certain speed, and we do have another group which located for I2 or located within another mesh that already roaming with a different speed. So the mesh current, it is different than the branch current. These are branch currents, but I1 and I2 here, they are not equivalent to the I1, I2 here in this case, right? This electrical circuit on the left, this is what we used to use for the electrical circuit analysis, using especially the first two methods. But for the new method here that we are going to discuss, the mesh current method, we have to identify this mesh current. So here, just to know the difference between these two approaches. For example, if we apply the Kirchhoff voltage law and current law to this electrical circuit, we're gonna end up with some equations, right? So if we apply the Kirchhoff voltage law to the first loop, this is gonna be loop 1. Here we're gonna have loop 2. We're gonna apply the first equation we're gonna end up with the first equation 1. When we apply Kirchhoff voltage law to the loop 1, then we're gonna end up with the second equation when we apply Kirchhoff voltage law to the loop 2. So these are loops, electrical loops, right? Then if we apply the Kirchhoff current law at node 1, at this node, we're gonna end up with this third equation. Then we can somehow solve these three equations or combine them together to end up with these two equations. Make sense? Then these two equations, you're gonna find that they already including I1, I2, which are some currents over the different electrical elements, right? Like all of these, like I1 and I2 and I3 in this case. Make sense? So this is for the first, if we apply the first method over this electrical circuit, and this is what we used to do, and here we defined loops. But how about the other method? If you just compare these two equations to these two equations, you're gonna find that they are identical, right? Very similar equations. So it means that the mesh current method, it can give us it is like kind of combination between the Kirchhoff voltage law plus the Kirchhoff current law in one law, which is the mesh current, kind of. Just to understand the difference between the two methods. For example, to apply the Kirchhoff voltage law and current law, you have to apply Kirchhoff voltage law, then the Kirchhoff current law, then you're gonna substitute the Kirchhoff current law into the Kirchhoff voltage law to end up with two equations. Like for example, you have to substitute with this term into these two equations to have another two equations. Like you already getting rid of the Kirchhoff current law or combining the Kirchhoff current law into the Kirchhoff voltage law by the substitution, right? So in the Kirchhoff current law, we can do so. We can combine Kirchhoff voltage law and current law in one law, which is the mesh current, to end up with the same two equations that we can get using the first method. Make sense? So we can understand that the mesh current method, there is like a combination between, like combining the Kirchhoff voltage law, Kirchhoff current law in one law, which is known as the mesh current. You could understand it in this way. So how this method is working, basically, the procedure is very simple. It is a very simple method. Step 1 is just to define mesh currents through the electrical circuit. Don't distribute the current as we used to do for the first two methods. Just identify or define mesh currents through the electrical circuit. So you have to locate the different meshes. Mesh, it is like a loop, but don't skip branches. So it means that we're gonna have one mesh here, there is another mesh here, there is another mesh here, there is mesh here, there is a mesh, a mesh, a mesh. All of these are meshes, right? And then identify the current within each one of these mesh. Like here, I'm gonna give I1, here, there, it will be I2, I3. You can start here, I1, here, I2, I3. The order, which one takes I1, which one takes I2, it doesn't matter. It means that for this electrical circuit, we have three meshes, and you're just gonna define a current over each one of these mesh. The same thing would have four, and you're gonna identify a current over through each one of these mesh. So this I1, I2, I3, I4, these are the mesh current. These are not the currents over the branches. So for example, how much of current already going over or through the R2? We don't know yet. It is not I1, it is not I4, it is not I2, it is not I3. Right? The same thing, how much is the current over R4? It is not, it isn't any one of these. It would be combination between one or two of these different mesh currents. So the mesh current is different than the branch current. So the first step is just to define this mesh current. Then you are going to apply the Kirchhoff voltage law for each mesh. You're just gonna write the Kirchhoff voltage law for each one of these meshes, and I'm gonna explain to you over this example how we can do it over this one. For example, here we identify two meshes, like this mesh 1 and this mesh 2. So if I ask you to write the Kirchhoff voltage law, for mesh 1. So let us just work over mesh 1. So for mesh 1, we do have three electrical elements, right? We do have a volt, which is VA, right? And we do have, there should be a current here, like there should be another volt over R1, and there should be another volt over R3. Make sense? All of this should be zero according to the Kirchhoff voltage law. But we have to decide for the sign, right? We said that in case that you do have the electrical element, this current I1 is already moving from the negative to the positive. So this is going to be like, according to the current direction, it should be positive. But since this one is input, so it's going to take a negative sign as we agreed, right? Then if we keep going with this one, you're going to find that I1, the current over this electrical resistance, it should be I1, and it goes in this direction, right? And I1 over this electrical circuit will be going in this direction, right? So for the voltage over R1, it should be positive because it is output. The same thing, the voltage over R3 should be positive because it is output. But the question is, no problem, we just carry on with the VA, which is the voltage over this battery or this electrical source. But how about the voltage over this resistance R1? This voltage over R1, it should equal, according to Ohm's law, it should be the current over R1 times the resistance R1, right? But how much is the current over R1? The current over R1, it makes sense that we can understand that the current over R1 is just I1. This I1, it is a mesh current, yes, but it is the same current over R1. Just for this case, just for R1. So it is just I1. So it means that I'm going to have here plus I1 times R1. This is the voltage over R1. How about the voltage over R3? For the branch R3, there are two mesh currents already interacting over the resistance R3. One mesh current, which is the I1, going in this direction, going down. This is the I1. And there is another mesh current that goes in the opposite direction, which is I2. If you, from the second, because this R3 is a common resistance between the two meshes, right? In this mesh and this, it works with both. So that's why, and as I explained to you, you can deal with this mesh current like two different currents, like two different groups of electrons. So you're gonna find some electrons already going in this direction, kind of, and you're gonna have some other electron going in the opposite direction, kind of. It is not physically this case, but you can assume that, like, we do have two different speeds, and these two electrons interact together over this branch, over this electrical element. So in total, the current over R3, it should be the difference between I1 and I2. Why the difference? Because they are moving into opposite direction. So one will be positive, the second one, it should be negative. But how about for some reason, if we do have an electrical element here or a branch, and for some reason, based on our distribution of the mesh currents, that we found that both currents are going in the same direction, so you're gonna sum them. Make sense? Which is gonna be a very rare case, but generally, in most of the cases, we have to take the difference between, we're gonna take the difference between two opposite currents over the same electrical element, between, in case that you have an electrical branch or electrical element that is already common between two different meshes. And like this case, like the case of R3. So the total current over R3, it should be the difference between I1 and I2. Is it I1 negative I2 or I2 negative I1? It depends on which direction. Where is your reference? So for example, the easiest way, since we're already working over mesh 1, so I'm going to take I1 as my reference. So in this case, I'm going to say that the voltage over V3 over R3, it should be the current over R3 times R3. So it's going to be R3 times the current. The current is going to be the difference between I1 negative I2 equals 0. Why I put the I1 positive? Because this is my reference since I'm working over mesh 1. Then I2 is going in the opposite direction of I1. It means that it's going to be negative equals 0. This is going to give us the first equation for mesh 1. This is just Kirchhoff voltage law, but we included the current law directly within this Kirchhoff voltage law based on the mesh current method. Make sense? Let us apply the same, but for the second mesh, for mesh 2. Let us work over mesh 2. If you apply the same, but for mesh 2, here we do have 3 electrical elements, right? One is a volt, which is this one. The second one, all of these are electrical outputs or resistors. So in total, we should have like VR3, and we should have VR4, which is the voltage over, or VR2, which should be the voltage over the second resistance or resistor. And in addition, we should have VB equals 0. Make sense? Again, for this mesh 2, our main reference, it will be I2 itself. So if we do have this I2 already going in this direction, so if I ask you, let us decide for the signs of these different sources or these different electrical elements. So for example, VR3, it should be negative. Why? It should be positive, I'm sorry, because it is output. And VR2, it should be positive, it is output. VB as well, it should be positive. Why it should be positive? Because if you can observe the direction of the current I2, it's gonna go from positive to negative. From positive to negative. It means there should be here negative, and since this should be a source, so negative times negative gives positive according to our method that we explained for the Kirchhoff voltage law. Make sense? So there are 2 signs basically that we have to decide for. The first sign is that I2 is already moving from positive to negative, so this takes negative. So we do have one negative. In addition, VB, it should be a source. A source, it should be input. Input, it should, as we agreed that we're gonna give it a negative sign. So negative times negative gives here positive. So that's why we do have VB here is positive, but VA, which is the other source, it is negative because of the difference in the polarity of how we set up these polarities within the electrical circuit. Make sense? But anyway, so we do have this. This is the Kirchhoff voltage law, but in terms of the voltage, we have to substitute for VR2, we have to apply Ohm's law. So how much is the current over R3? The current over R3, it will be the difference between I1 and I2 as we agreed, because we do have 2 different mesh currents going through the same branch, right? But what is our main reference? In this case, our main reference, we're gonna consider it the I2 since we're already working over the mesh 2. So I'm gonna say that the voltage over R3, it will be R3 times the I2 negative I1. Plus, how much is the current over R2? R2, it is included within only one mesh. It is not common between 2 different meshes. So it means that R2, the current over R2 definitely it will be just I2. Make sense? So is gonna be just I2. So we're gonna have the voltage VR2, it will be R2 I2 plus VB equals 0, and this should give us the second equation. If you just compare equation 1 to this equation 1, this should be the same equation, right? So we already have just move VA, so we can have VA and R3 I1 negative I2 plus I1 R1. But for the second equation also is gonna be the same. This is gonna be the second equation where this one is negative R3 I1 negative 2. If you multiply this negative inside, so it's gonna be I2 negative I1 plus R2 I2. Then if you move VB to the other side, it's gonna be negative VB. So we got the same 2 equations, and this is how the mesh current method is already working. You should understand that the mesh current, it is like combination of, like we're already combining directly, applying Kirchhoff current law and voltage law in one equation directly. This allows us to skip applying the Kirchhoff current law, and it will be automatically included within the Kirchhoff voltage law. So we're gonna skip one step that just apply the Kirchhoff voltage law. You're gonna end up with the two equations directly like the first method. This is the basic idea of the mesh current. So in the procedure, as we said, define the mesh currents, then apply Kirchhoff voltage law as I explained above for over each one of these meshes. It means that for each mesh, you're gonna apply the Kirchhoff voltage law, you're gonna end up with one equation. For example, if you have three meshes, so you're gonna end up with three equations. If you have four, we're gonna end up with four equations, and so on. Then your objective is just to solve these four equations, or three equations, or two equations for the mesh currents. What are the mesh currents? Which are the I1, I2, I3, I4. Once you find these mesh currents, you can use them to figure out the currents over any one of these electrical elements easily. Make sense? So this is how it works. Then once you find these are the main three steps, then you have to use this mesh current to find the voltage or the current over any electrical element depending on the requirement of the problem. So as a practice over this case, it is a very simple problem. Let us consider this example here, example 1. Of this electrical circuit that include 3 resistors in addition to 2 voltage sources. So the first step, as we agreed, that we are going to set up some mesh currents through the electrical circuit as we basically did here. Already I1 is the first mesh current, and I2, this is the second mesh current. Make sense? Then your objective is just to apply the Kirchhoff voltage law to each one of these currents. It is very simple. So step 1 is just define mesh currents. Mesh currents. And we already did, right? The second step is just apply Kirchhoff voltage law to each mesh. Make sense? So let us start with mesh 1. For mesh 1. In mesh 1, we already have here 3 electrical elements, but you have to have a look to the electrical element that is already common between two meshes, right? Like the 10 ohms. This 10 ohms is already located between two, or common between the mesh 1 and mesh 2. So what I'm gonna do, you have to figure out the direction of the current. So the current over the 10 ohms, according to the mesh 1, it should be I1 going down, right? But the current over I2 should be going up. So it means that the total current over this branch, it should be the difference between I1 and I2. Make sense? Depending on which reference, it would be like I1 negative I2 or I2 negative I1, depending on your reference. So here we are working over mesh 1. So mesh 1 is going to be our reference. So if I ask you how many voltages that we should have for this electrical circuit, in total we do have 3 voltages. We do have the 150 volt, which is the source volt. And as you can see, I1 is going from the negative to the positive, right? So it should be positive times that there is another sign that it should be negative. Why negative? Because it is input. This is the input source. In addition, so this is the direction of this current. So the 150 will be negative. In addition, I1 will be the current over the 20. The current over the 20, just I1. It is not a common current on this. We do have only one flow of current through the 20. So it's going to be the 20 times I1. This is the voltage over this electrical element. And since it is output, so it's going to take positive according to our approach. In addition, we do have another electrical element within this loop, because this here, we're going to deal with this one like a loop, since we're already applying the Kirchhoff voltage law. So within this loop, we do have the I1 negative I2, because our reference, it will be I1. So it's going to be 10 times I1 negative I2. And this should be positive as well, because this should be an output electrical element. All of this, it should be 0. So this is going to give us the first Kirchhoff voltage law to the first loop that based on the mesh current method. Then we're going to apply the same for mesh 2. For mesh 2, we do have 3 electrical elements. We do have the 10 times. How much of the current over this one? It will be I2. In this case, it will be I2 negative I1. Why I2 negative I1? Because our reference in this case, we are working on mesh 2. So our reference will be I2. So it's going to be our I2 negative I1. Why? Because they are moving into opposite directions. And this one should be positive. Why? Because it is output, it is resistor. Plus, there is another electrical element which is resistor of resistance 15. And how much is the current over the 15? It will be I2. So it's going to be 15 I2. How about the voltage over this electrical source? Voltage source, it is 100, but it's going to be positive. Why is it going to be positive? Because it should be like negative times negative. Because the current I2 already moving from positive to negative, so this takes negative. In addition, it being like output source or a source, it should have another negative, so it's going to be positive equals 0. Make sense? And this is going to give us the second equation. So as you can see, we're already having two equations in just two unknowns, which are the I1 and I2. Your objective is just to solve these two equations for the I1 and I2, which are the mesh currents. So simply solving these two equations for the two unknowns, we're going to end up that I1, we're going to find I1, it will be 4.23 amperes, while the I2, we're gonna get it by the negative 2.308 ampere. Make sense? So these are the these are the mesh currents. These are the mesh currents. So for example, if I ask you just to identify the currents over all of these electrical elements. We do have in total 5 electrical elements. So what is the current over this voltage source? How much of the current over the 20? How much of the current over the 10, the 15, the 100 voltage source? So to do it, basically, we have to use these two mesh currents. And as you can see that I2, it has a negative sign. Negative sign here that it means that we have to switch the direction of the I2. In the beginning, and this is something that I missed to, I forgot to tell you about it, that we basically assume any direction of the current, but make sure that you assume all of these currents already roaming in the same direction. It is advised to assume one direction for all the mesh current. Like, it doesn't matter, for example, if you switch the direction of I1 and the same thing for I2, no problem, you're gonna end up with the same result. So just pick any direction, and normally what we used to assume for the loop voltage analysis using for the loop, for the Kirchhoff voltage law, we assume the clockwise direction, so you can follow the same instructions here or the same procedure, right? So going back to this question here, how much of the current over this 150 voltage, how much of the current over the 20? So it does make sense that the current over the 150, it is already going in this direction, and it is totally I1, which we already got it by 4. So we're gonna say that it is 4.23. Should be the current, right? So let me draw this electrical circuit very quick down here, or just copy this one. Then I'm gonna distribute the currents over all of these electrical elements. So we already have this is the electrical circuit, and let us distribute or define the branch currents. What we got here, these are the mesh currents. How about the branch currents over all of these electrical elements? So as we agreed that we're gonna have a current that is going in this direction, and it should be I1. I1, which we already got it, equals to the 4.23 amperes. This is the current over the 150. How about the current over the 20? It should be the same. The same current is gonna keep roaming, keep rotating here. It's gonna be the 4.23 ampere as the I1 as well. But how about the current through this resistor or this resistance? If I ask you to distribute the current as we used to do for the Kirchhoff voltage law, the first two methods, we should have a current here, the total current, which it should be the 4.23, and then this current is going to be split into two parts, right? You're going to have one current going in this direction. So it means that this should be our main reference, and there should be another current going in this direction. If you divided this current through this node, right? So how much is the current through the resistance are 10 ohms? It should be the difference, as we agreed, it should be the difference between I1 negative I2, or it would be I2 negative I1. But based on the current distribution over branches, the current, it should be going down, right? So it means that the one that it should be going down, it is parallel. It should be like I1, right? here, and there should be like I2 going up. So it means that I1 is positive because in the same direction that we have to consider for the current negative I2, right? So if you decided to apply here this one, so the current, this current over the 10 ohms, this current, it should be the I1 negative I2 equals, how much is I1? We got it by 4.23. Negative becomes positive, the 2.308, which if we sum these two numbers, this is gonna give us 6 point something, right? It's gonna give us 4.23 plus 2.308. This gives us the 6.54, for example, ampere. So this is gonna be the total current over this branch, and it should be going in this direction. But how about the current over the 15? The current over the 15, it should be just I2, right? It should be I2, but you should keep in mind that I2 according to this loop, it should be going in this direction, but I2 we got it negative. So the correct direction of the current over the 15, it should be opposite. It shouldn't be this one. It should be switched in this direction to be I2 that we got it by 2.308. And also, as you can see, we're already switching the direction. I2 was going from the positive to the negative through this volt, but now we got I2 is negative. It means that the correct direction of the current over this voltage source should be going up, opposite to the I2 that we got because of this negative sign, equals to 2.308. So what does it mean? It means that in this case, this source gives current of 2.3 that goes in this direction, while this source already giving another current of 4.3 that goes in this direction, and both of them already combined together to feed, kind of like, because the two currents already going to the same node and collected and summed together to feed this 10 ohms resistance here, then these two currents will be distributed back. It means that this 2.3 is gonna return back to this source, and this one will return back to this source, and you're gonna have the electrical circuit still feeding and still working. Make sense? So this is the method. Like, we come up with the mesh currents, then we can find or do some simple calculations to identify the currents over all of these different branches of the electrical circuit. Make sense? So this is for the first example. Let us consider another example. The difference between this one and the previous one, actually, that here in this one there is no, both these two sources, both of them are voltage sources, but here we do have a current source in this second example. So how it's gonna work, let us consider this example. So for this one, here, the first step as usual, just define the mesh currents. We do have here like two loops, so we're gonna have one mesh and there is another mesh, and we're gonna define here like I1, I2, and assume that the direction of these two meshes going in the same direction in the clockwise direction. Make sense? So we already defined I1 and I2. Then your objective is just to apply Kirchhoff voltage law to each one of these mesh, right? But if we try to apply the Kirchhoff voltage law over the first mesh, we cannot, because we have no clue how much of the voltage over this current source. This is a current source. We knew the current, how much it is 2 ampere as given here, but we have no clue how much is the voltage over this electrical source. So what does it mean? It means that if we try to apply the Kirchhoff voltage law at this instant over this first loop, we cannot do that. So it means that we have to figure out how much is I1 based on the source current. And it is gonna be much more easy. If I ask you how much, according to the mesh current that I defined here, over this first mesh, which is I1, the current over this electrical source, it should be I1, it should be going. And if I ask you how much is the current of this electrical source, you have to tell me that it should be I1, and it is already given by 2 ampere. So we can conclude directly that I1 equals 2 ampere. And this is the key idea here. So it means that there is no need to apply the Kirchhoff voltage law to the first mesh, because we knew the value of the I1 based on this given source as 2 ampere. But how about for some reason, if the direction of this current source is switched, like it is already given down, so it should be negative 2 ampere. Why? Because I1 that I assumed as a mesh current is going in a direction that is opposite to the real current that already delivered by this source. It means that we're gonna have a negative sign here. Make sense? But since in this problem they both are in the same direction, I assume I1 that by chance it became in the same direction as the 2 ampere, which is the current source. That's why I1 automatically it will be 2 ampere. Now I can move to the second mesh and apply the Kirchhoff voltage law to this, just to the second mesh. And this is what I'm gonna do. So I'm gonna apply the Kirchhoff voltage law, but for just mesh 2. For mesh 2, we have 3 electrical elements. If I ask you how much is the current over the 10 ohms, you're gonna tell me, remember that I'm working over the mesh 2. So it's gonna be, as you can see, I2 is going up, but I1 is going down over this branch. So it should be the difference. But I2 negative I1 or I1 negative I2 depends on which reference. We already working as mesh 2, so our reference is gonna be I2. So it means that the current, the voltage over this source, over this electrical element 10 ohms, it will be I2 negative I1 times 10 ohms. This is the voltage over this one, and it should be positive. Why positive? Because it is output. Then there is a voltage over this one, which it should be I2, because the current over the 5 ohms, it should be I2 going in this direction. So it's gonna be also positive because this is output as 5 times I2. Then how about the voltage over this one? It is 10 volt, but is it positive or negative? Because this is a voltage source, so automatically it's gonna be 10 volt. But in this case, it should be positive. Why? It's gonna take a negative sign because the I2 going from positive to negative, so it's gonna take a negative sign, and since this is a source, it should take another negative sign, so negative times negative gives positive equals 0. So we're going to end up with just one equation and just one unknown, because you have to understand that I1 is already given by 2 amperes. So if you substitute it here and solve for I2, we're going to find I2 equals 0.67 ampere. This is the mesh current, the second mesh current, and this is the first mesh current. So as we did in the previous example, if I ask you how much is the current over the 10 ohms, for example. So this current, according to the distribution, we should have like, there is a source here which delivers 2 ohms, 2 ampere of current. So we should have here like total current here. This is the I source. Like work like you distribute the current as we used to do for the first 2 methods. Then at this node, this source will be split into 2 currents. One current is gonna go over this 10 ohm resistance. The 10 ohm, it should be the difference between I1 and I2. And as you can see that this is the direction that I'm considering for the current based on the conventional distribution of the current through the electrical circuit. And this one is the same direction as I1. It means that I1 it should be positive, but opposite direction to the I2, so I2 it should be negative to define the current over the 10 ohms. I1 I got it by 2, I2 I got it by 0.67. So it's gonna be 2 negative 0.67, which gonna give us the 1 point as a current equal to 1.34 ampere. This should be the current over the 10 ohm resistance. But how about the current over the 5 ohms resistance? It is the 0.67, which is I2. How much is the current over this voltage? It is 0.67, and it going down 0.67 as already given here. Make sense? So this is for the second example, and it is very easy, very simple example that we considered here. Make sense? All right, so let us consider this example 3 for this electrical circuit that include 2 sources. One is a current source, the second one is a voltage source. So as usual, we are going to define I1 as the first mesh, and we gonna define I2 as a second mesh, and we're gonna have here like I3 as a third mesh. It doesn't matter which one is I1, which one is I2 or I3, the order it doesn't matter, but the key idea, we're gonna have 3 meshes here, and we have to solve this electrical circuit or do analysis to this electrical to come up with the values of I1, I3 and I3, these mesh currents, right? It means since we already have 3 mesh currents, it means that we have to draft 3 equations to solve these 3 currents. So, and we used to apply the Kirchhoff voltage law. So if I ask you to apply the Kirchhoff voltage law to the first mesh, we cannot do it. Why? Because simply there is a current source here, and we have no clue how much is the voltage over this current. The same thing applies to the second loop or the second mesh. The second mesh, there is no ability to apply the Kirchhoff voltage low to the second mesh because we don't know the voltage over this current source. So it means that we're already losing two equations. We have only one equation that we can easily apply Kirchhoff voltage law to this loop. So we have only one equation so far. How about the other two equations that we have to find them to solve for the three unknowns? So we need three equations. We already have one by applying the Kirchhoff voltage law to this mesh. But how about these two meshes here? So we can, if I ask you normally, like proceed as usual, if I ask you to apply the Kirchhoff voltage law to this electrical circuit, you're gonna skip this branch, right? And then you're gonna apply Kirchhoff voltage law over this big loop. And we're gonna do the same. So this is gonna give us another equation, right? So we're still looking one more equation and we're gonna figure this equation later. So now let us skip this branch just for now and apply the Kirchhoff voltage law to this loop, big one. So if we did so, we're gonna apply here the Kirchhoff voltage law to this loop. Since we're already working in the mesh current method, we said that we have to apply Kirchhoff voltage law to each mesh. So we're gonna give this one a name as a super mesh. It is commonly known as the super mesh. A super mesh is the one that include a current source in between. So we have to skip this one and then we're gonna do analysis for the overall loop, like the overall mesh. As we discussed before, there is a difference between the concept of a mesh and a loop. So that's why, as I told you in the beginning of this video, that we cannot skip a branch, especially in case this branch it has like a resistance or whatever, right? But in case that we have a branch that include a current source like this one, we can skip this one and then we can apply. And in this case, we're gonna have a special mesh which is known as the super mesh. Make sense? Forget about the name of this mesh, just apply Kirchhoff voltage law to the super mesh as given here. So what we're gonna end up here, so how much is the voltage over this one? It will be 1 ohms times the current over this resistance. The current over this resistance, it should be I1. The current over this resistance should be the difference between I1 and I3, because there is I3 is going to affect here, right? So if we just consider, let us just draw very quick the currents over all of these elements. So there should be here I1 and there should be here I1 going in this direction, and there is I3 going in the opposite direction. This what should be over the 2 ohms. What about the current over this one? The current over this, forget about this branch for now. The current over the 4, it will be 2I2, and I3 is gonna be in the opposite direction. It's gonna have here I3 going in this direction according to the I3 definition, right? So going back again to the Kirchhoff voltage law, the voltage over this electrical element, it will be definitely 1 times I1. So it's just gonna be I1, and it should be positive. Why? Because this is output source, output element. And how about the voltage over this one? It's gonna be plus, because it is output, 2 times our reference is I1, since we're already working over this loop. And this loop, all of this I1 and I2, both of them are rotating in the same direction. So our main reference is the rotation of I1 or I2. So I1, it should be positive, but the I3 is the negative one. I3 is negative because it goes in the opposite direction of I1. Then what? So we got the voltage over this element. The voltage over the 4, it should be plus 4. Plus, because it is output, it is 4 times I2, which is our reference, negative I3. Make sense? And there is another voltage source here that it should have 10 volt. Should have 10 volt. Is it positive or negative? It depends. It depends on what the current over this voltage will be I2, and it's moving from positive to negative, so it should be negative. And since this is a source, it should have another negative, so it should be positive, equals 0. This is gonna give us the first equation, that we apply the Kirchhoff voltage law to this super mesh. Make sense? So this is one equation. How about the second equation? We need one more. So this is the first equation. Now we are going to apply the Kirchhoff voltage law, but for mesh 3. If we did so for mesh 3, it had 3 electrical elements and all of them should be outputs because they are resistors. So we're gonna have here for this one, the voltage over this one, it will be 2 times I3 is the one that it should be positive in this case, because our reference is going to be I3. We move to the mesh 3. So I3, it will be positive, negative I1, because it goes in the opposite direction. And we do have here plus 3 times I3, because the voltage over this one, it will be 3 times the current over it would be just I3. And the current over this one, it will be I3 negative I2 times 4 to give the voltage. So it's going to be plus I3 negative I2. All of this should be 0. And this is going to give us the second equation by applying the Kirchhoff voltage law to the mesh 3. So we're still making one equation. We need one more equation. This one more equation, it depends on this branch that we skipped here, which is the current. If I ask you how much is the current over this branch, you're gonna tell me that this current, it will be I1 going in this direction, right? While I2 going in the opposite direction. So what does it mean? It means that the current over this branch, it should be I1 negative I2 or I2 negative I1. Which one it should be positive? Which one it should be negative? I2 is the positive one. Why? Because the 5 ampere is the current going up. So our reference in this case, it should be I2. It means that, and this is going to give us the third equation. If I ask you how much is the current over this branch, it should be I2 negative I1, which is already given here for this current source by 5 ampere. Make sense? So this gives us the third equation. So we end up with 3 equations that can be simply solved for these 3 unknowns, which are I1, I2, I3, to find them. So to solve this equation, we have to arrange these equations, these 3 equations, in like I1 plus I2 plus I3, just arrange them. Then you can use the calculator to solve this equation. So for the first equation, for example, in total, we do have 3 I1s, right? 3 I1. So it's going to have here 3 I1. Just I'm arranging these equations. I2, it's going to be 4 I2 plus 4 I2. I3, it's going to be negative 2, negative 4. This gives in total negative 6 I3. Then I'm going to move the 10 to the opposite side, to the other side, which is the negative 10. And this is going to give us the first equation dash, the new form of the first equation. Then the second equation, do the same. Here we have negative 2 I1 and nothing else. So we're going to have negative 2 I1. For I2, for the second equation, we do have negative 4, only negative 4 I2. The third equation, we do have 4 I3, 3 I3 plus 2. So this 5 plus 4 gives 9 I3 in total equals 0. And this is going to give us the second equation. Make sense? What else? How about this equation? The third one, it is very simple. It is negative I1 plus I2, but 0 I3. There is no I3 equals 5. This is going to give us the third equations. Solving these 3 equations for I1, I2, I3, we can find them, which we're going to get them very simple. I'm going to use the calculator very quick. So equation 5, solving for 3 variables. And we do have 3 I1, 4 I2, and negative 6, and then negative 10. And for the second equation, negative 2, negative 4, 9, and 0. And we do have negative 1, 1, 0, and 5. Solving, we're going to end up with I1. It's going to be I1 will be negative 5.56 ampere, while I2, it will be the negative 0.56, while I3, it will be the negative 1.48 amperes for sure. So we got all of them negatives. It means that there is something, it means that we have to switch the direction. It means that the correct directions of the current should be opposite to what we already proposed in the beginning, or assumed in the beginning of this problem. So this gives us the total currents over the mesh currents. If we are interested in the current over any one of these electrical elements, like for example element 2, how much is the total current over element 2? It's going to be the difference between I1 and I3. So if you just subtract I1 negative I3 or I3 negative I1, this is going to give us the current over this electrical element, and so on for the others. Make sense? So this is for this example. So let us consider this example here of this electrical circuit that include two resistors, 400, 200 ohms, in addition two sources here. This source is a current controlled current source. Why it is current controlled? Because the current of this current source, it is a function of the current itself. So it is current controlled current source of its current. It is 4IB, where IB, it should be the current over this 100 ohms. And you should understand that the current of this 100 ohms, it should be the total current over the real total current over this branch. So IB, this is a branch current. You should understand this. Notice there are some important notes here. We distinguish in the beginning of this lecture between the current, the mesh current and the branch current. So IB here, IB, it is a branch current. This is the branch current. This is the current over the branch, which is this one, but which is not a mesh current. Then if you decided to proceed of solving this problem, it's gonna be very simple. It means that we have to set up like the mesh currents over the different meshes here or different loops. So we have like one mesh here, we can set up one mesh here, and there should be another mesh over this side, right? But as you can see, generally, for example, I can set up here, like I'm gonna assume that there is one I1 and there is another current which is IA or I2, for example. So I1 and I2, these are I1 and I2, these are the mesh current, these are mesh currents. So you should understand this point, that it is not necessary that IB, it should be I1 or I2. It depends. It depends on what? It depends on the current that you already, or the mesh current that you're already assuming or considering or proposing for this electrical circuit. But the IB, this is the branch current. And this current source, it depends on the current over this branch current, over this electrical element, which is the branch current. So the IB here, it is a branch current, it is not I1, it is not I2, right? So generally, let us proceed. The first step is just to define mesh current. So we define two meshes here, I1 and I2. Then your objective is just to find I1 and I2 normal. Just proceed conventionally, as we used to do. The new idea here of this type of problem, that the dependent source, as we agreed that the dependent source is going to depend on the current or the voltage of another element. But you should understand that this voltage of the over the other element, it is the general volt, that it is not the same one that depends on the mesh current. So it's gonna be clear if we proceed for solving this problem. So let us proceed. The first step is just to apply the mesh current here. We define mesh currents, two meshes. Then your objective is just to apply Kirchhoff voltage law to these loops or two meshes to come up with two equations, because we are interested in two equations, because we do have two unknowns, two main unknowns, which are the mesh currents I1 and I2. So we have to apply Kirchhoff voltage law to both of them or just one, it depends. So for example, if I ask you to apply the Kirchhoff, can we apply Kirchhoff voltage law to the first loop? No. Why? Because we have no clue how much is the voltage over this element, but we can find the voltage. It is not given to, but anyway, we do have the current element or the current source, and we said that the voltage over this current source, it is not given. So we have no clue how much is the current source, how much is the voltage over this current source. Make sense? But the good thing that we should understand that I1 equals IB. I1 equals IB. Why I1 equals IB? Because it is, if I ask you how much is the current over this electrical element, over this branch, it should be I1 in terms of the mesh current. So the current over this branch, or the branch current over this electrical element, in terms of the mesh current, which is I1, it should be I1. It means that from this first loop, from mesh 1, we're gonna conclude that I1, it should equal to the 4IB as usual. And this is gonna give us the first equation. Make sense? Now we are interested in the I2, how much it is. Assume in the beginning, like IB, it is given. So to me, I1, I got it. I got I1, that's it for now. Then we have to proceed to the second mesh. The second mesh here, we can apply the Kirchhoff voltage law because we do have volt over these elements. So we're gonna apply the Kirchhoff voltage law to the second mesh, to mesh 2. So here we do have three voltages, one over the 100 ohm, one over the 200 ohm, one over the 8 volt, right? So we do have here the 100 should be positive because it is output. So it should be 100. If I ask you how much is the current over this resistance, the current over this resistance should be IB in terms of the branch current. Forget about the IB for now. Skip the IB. Work like you're already working as mesh current. So this mesh current, the current in terms of the mesh currents over this resistance, it should be the difference between I1 and I2. Make sense? I1, which one is going to be our reference? Our reference is going to be I2. So it means that it's going to be I2 negative I1. As forget about the IB. It's just a number and skip this number for now. Make sense? So it means that we have I2 negative I1. This should be the current over this branch. Make sense? So we got this current. We got this voltage over this element. How about the volt over this element? It should be positive because it is output 200 but times I2 equals we still have this volt. This voltage is 8 volt. Is it positive or negative? The current I2 goes from the positive to the negative, so this gives a negative sign, and since this is a source, it has another negative, so it will be positive equals 0, and this is gonna give us the second equation. So now we end up with two equations in two unknowns. You got my point? Or basically in total we do have like three unknowns. I1 in the second equation we do have I1 and I2 is unknown, and I1 in terms of IB. So simply we can plug I1 from equation 1 into equation 2. So we're gonna end up with another equation of I2 but in terms of IB. Make sense? So in total through this equation we do have three unknowns. These three unknowns are I1, I2, and IB that we consider like it is given in the beginning, but it is not given. It is actually unknown, and we are seeking value for IB. So how much is IB? How we can get it? IB, what is the IB? IB, this should be the current over the 100 ohm branch. It should be the current over this branch. So if I ask you how much is this current IB over this branch, it should be the difference between I1 and I2. But this difference between I1 and I2, is it gonna be I1 negative I2 or I2 negative I1? It's gonna be I1 negative I2. Why? I'm gonna consider because I1 in the same direction of the IB, but I2 in the opposite direction. So it's gonna be positive I1 negative I2. This is gonna give us the current over this branch, which is IB, and this is gonna give us a third equation. So we're gonna end up with three equations in three unknowns, which are the I1, I2, and IB. Simply can be solved to find them. Make sense? So in case that the key idea here, in case that you do have a dependent source, whatever it is, dependent source like this source, it is current or voltage. Dependent, it means that it's going to depend on the current or the voltage of another element within the electrical circuit. You should deal with this current like IB, or if it is voltage, like this is the pure or the overall voltage over this element that is independent, that does not depend on the mesh current. So you're gonna apply the method as it is in the beginning. Assume that this current IB is like given. But in fact, it is not given, so you need an extra equation. You can figure out this extra equation from the information that provided. For example, like IB, it should be the current over this branch, over the 100. And your objective is just to find IB in terms of the mesh currents that you defined or you assumed in the beginning. So solving these three equations, we're gonna end up with I1. So let us just arrange this equation. From the first equation, we're gonna have I1 negative, or let us just, if we solve these three equations, we're gonna end up with I1 equals and I2, then we can find the IB in terms of amperes, right? And this is basically what we're gonna do. So I'm going to solve these three equations. So after solving these three equations, we found that I1, it should be negative 0.029 ampere, while the I2, we're gonna get it by the negative 0.036, and IB will be the like almost zero. It's gonna be 0, 0. Sorry, let me. Yeah, it's gonna be 0, 0, 0.27 ampere. Make sense? So this is for this problem. As you can see that IB is different than I1 is different than I2. It should be it should be dependent on the difference between these two mesh current that we assumed in the beginning. And you should understand that I1 it should be 4 times IB. If even you double check here, if you divided 27/4, this should give us this value that we got for IB, which it should be, if we divide it, it's gonna be 0.0027. It should be 72. I'm sorry. Yeah, it should be 72, not 27. I just, like messed up the numbers. So it should be 72 amperes. If you multiply this number times 4, this is gonna give us I1. But here, these signs indicate that these directions of these mesh currents, it should be opposite. So in total, the current over this 100 ohm, it will be IB, which we got it by the 0.072, and the current over, for example, this 200, it will be I2, and it should be the 0.036, which it should be opposite to this direction. It should be rotating opposite to this direction. It means that it should come from the source and going in this direction. Make sense? So this is for example. The key idea again is it depends on just you have to consider this one is a dependent source, and the current here is the total current over this branch, that it is not I1, it is not I2, which are the mesh current that you are going to assume. Make sense? Now let us consider a typical or a very similar example here of this one, but this one here includes a controlled voltage source, and it is current controlled voltage source because it is 50 IB, and IB it should be the current over this resistance. It's going to be a very similar example, but there is a difference in the type of the voltage source or the controlled voltage source that we're already using. So we're going to do the same. You should understand that this IB, which is the voltage over 50 IB, and this IB that it define the voltage over this controlled voltage source, it is current controlled voltage source. This IB, it is the total current over this branch, which it should be independent, or it is related definitely to the mesh current, but it will not be the mesh current over this mesh or this one. So what I'm gonna do, I'm gonna again just assume mesh current like I1, and there is here another mesh current that goes in this direction as I2. Make sense? So we have two mesh currents that we have to work over them and figure them out. So we need two equations, mainly just work conventionally, like already applying the mesh current method. So if we try to apply the Kirchhoff voltage law to the first loop or the first mesh, we won't gonna able because we do have an electrical current source here. So we have no clue how much of the voltage here. So, but the only option that we have, that we should understand that I1 it should equal to the 60 micro ohm ampere. This M stands for micro ampere, mean that this value to be in terms of ampere, it should be divided by 1000. But anyway, it's gonna you should understand that I1, and this is gonna give us the first equation, it should equal to the 60 micro ampere as already given here, which it should be the 60 times 10⁻³ to convert to ampere. Make sense? So this is for the I1. It means that we are pretty sure how much is I1. Then let us move. So we got I1. We still missing the I2. So we have to apply the Kirchhoff voltage law, but for the second mesh, for mesh 2. For the second mesh, we do have three elements. This one is an output, so it should be positive. The voltage over this element will be 100 times I2 negative I1, I2 negative I1. Again, why I2 negative I1? Because our reference is mesh 2, so our reference is I2, and I2 going in this direction and I1 is the opposite to the I2, so that's why we do have the negative here. How about the voltage over this element is already given in terms of as V0. You can even just assume V0, or you can substitute by its value as 50 IB. It's up to you. And as you can see that I2 goes from the positive to the negative. So there is a negative sign here, and the value is 50 IB. This is the voltage over this voltage source. But since this is a source, it's gonna take another sign, another negative. So negative times negative gives positive, and we do have this is an output, so it should be positive 250 times the current over this element, which it should be just I2 equals 0. This is gonna give us the second equation, or just the first equation, because if we consider this is the first equation, this is gonna be the second one. So as you can see in this second equation, we do have three unknowns. I1 we already got it, so it means that we just have two unknowns, which are the I2 and IB. So if it means that we still missing one more equation. This one more equation we can figure it out in terms of the IB, which is the current that already given over this branch. So if I ask you how much is the current over this branch, it is already given as IB, and IB it should be I1 negative I2, typically the same as we did in the previous example. Why I1 is positive, I2 is negative? Because I1 in the same direction of IB, but I2 is already in the opposite direction. This is gonna give us the third equation. So from equation 3, this is very simple problem. From equation 3, IB we have no clue how much it is. I1 we got it by 60 times 10 negative 3, right? And negative I2. So this is gonna give us a relation that we can conclude that then we can substitute into equation 2. Into equation 2. So we do have here 100 times I2 negative I1, which is 60 times 10 negative 3, right? And plus 50 IB. 50 IB, this is all of this term is just IB. So it's gonna be 50 times 60 times 10 negative 3. Then we do have negative 50 I2. Then we do have the third term, which is 250 I2 equals 0. Make sense? I just substituted here for I2, just I2 negative I1, which is 60 times 10 negative 3, plus 50 times IB, which is 50 times this term, negative 50 times this term, plus 250 equals 0. So we're going to end up with one equation in just one unknown, which is I2. So we can solve this equation for I2 that we're going to get in terms of ampere. So simply solving this equation, and after we solve this equation, we can find, we already got I1, we can simply find I2 from this expression in terms of ampere as well. So solving this equation, so if we solve this equation, we're gonna end up that I2 equals 0.01 ampere, which is 10 microampere. Then substitute, plug into this expression here. Plug into this expression, you're gonna find IB. IB will be 60 times 10 negative 3 negative 0.01. This is gonna give us 0.05 ampere. Then if you multiply IB times 50 to end up with the V0, because it is 50 IB, we're gonna end up with the volt over this source by 2.5 volts. And that's it for this example. So, and that's it for this lecture, in fact, because we already finished these two examples. And the key idea in case that you have a dependent source, that the current or whatever it is that included over the dependent source should be the current or the voltage over the branch itself. So this is an important knowledge that you have to consider through this this type of problem. So by this method, we should be finished of chapter 2. There are a few things that we skipped for now that had been covered in chapter 2 in the textbook, but we skipped these parts that because definitely we're gonna consider them in as we move through the course. In the next meeting, we're gonna start a new chapter and we're gonna discuss the capacitors and the inductors in general, and we gonna consider more general application in case that we have electrical circuit that includes capacitors and inductors as well. What we discussed so far, we applied this 4 method that we're gonna use them a lot through the course. but we applied them just for resistive circuits. So we took enough time to give you more examples and more practice over these four methods. And in the next meeting, as I said, we're going to move to another chapter discussing the inductance and the capacitors. Make sense? So that's it for today, and thank you, and see you in the next meeting.